So carrying on from talking about work, we're going to move into energy. And the two are very related because energy is just the ability to do work. So remember, work was the dot product of a force and displacement. And remember, dot product means that those two vectors need to be going in the same direction. So work is a force over a distance, and energy is the ability to actually do that work. And we're going to primarily look at two different types of energy over the next week. Those two types are potential energy, and sometimes we shorten that to PE. And you'll also, let's do this. You also might see it written energy P. That's supposed to be an E. So potential energy is the first type. And potential, just like the name suggests, is it's energy that's not being used. It's stored energy. So that energy is stored and can be used to do work. The other type of energy that we are going to look at is kinetic energy. And unsurprisingly, based on what you've done in this class so far, kinetic is going to be talking about movement. Sometimes we shorten this to KE for kinetic energy, or you might see it written EK for kinetic energy. And this is energy of motion. So let's look at just a simple example. Let's draw the ground here, and we've got a ball. We've got a ball, and it's somewhere up here, right? We've got gravity working on pulling it down, right? So we've got Fg here, force of gravity. That's definitely a ball. That's supposed to be circular. So if it's just, let's say we lifted it up, it's in our hand right up here, it's not moving. Well, let's talk about these different types of energy. Potential energy is stored energy. Do you think it has some potential energy? Absolutely, because what happens if I take my hand away? It's going to fall. So it has some amount of potential energy. What about kinetic energy? If my hand is underneath it and it's not moving? Well, kinetic energy is energy of motion. So what do you think about kinetic energy? Well, it's going to be 0 because it's not moving. So what if, time goes along, I take my hand away and it drops. Now it's half the distance above the ground. We still have the force of gravity on it. That's the only force acting on it right now. What do we know here? Does it still have some stored energy, some potential energy? Well, yes, it does, because it can continue to fall, so it's going to be able to use energy. Remember, this force is acting over a distance, so that is work that's going to be done. So does it still have some potential energy? Yes. It has less potential energy than it had before, but it does have some potential energy. What about the kinetic energy? Well, is it moving now? Yes, so it has some kinetic energy. We haven't put in any values here yet because it's important that we actually understand what's going on. What about right as it hits the ground? So this is as it hits the ground. So not after it's stopped, but as it actually hits. So what about potential energy? Does it have any more stored energy? No. The potential energy is 0. What about kinetic energy? Is it moving? Well, yeah, right the split second when it hits the ground, it is moving. It's dropping at its quickest speed. So if it's traveling faster because gravity accelerates it downward, what do you think about the amount of kinetic energy down here as compared to here? Well, it's moving faster, so unsurprisingly, it is going to have more kinetic energy. So we'll have more kinetic energy. Just this simple setup here, you can see we convert all of our energy from potential energy and no kinetic energy to right here, converting it all to kinetic energy and no potential energy. And that actually leads us into our next point here, is that so long as there's nothing happening that's affecting it other than just this force of gravity, then the amount of energy at all these points is actually the same. It's just in different forms. And what we call that is the law of conservation of energy. So we're going to write out this definition. So in an isolated system, that just means there's no external forces acting on it. The total energy, and how could we write total energy? We could say the sum of all types of energy here, right? So the sum of the energy, or the total energy, remains the same regardless of any interactions within the system. So what that means is, system. So what that means is so long as we don't have anything outside the system acting on it, it doesn't matter what goes on inside the system. And by system, I mean what we're looking at. So in the last case, it was the ball, right? And the ground that it was interacting with. So long as there's nothing else interacting with it outside of that system, then it doesn't matter what goes on inside the system. The energy will always stay the same, the total energy. It may be in different forms at different points, but all that energy should remain the same. That is the law of conservation of energy. And we know the word law means that this is a very, very strong statement. So let's look at the application of this. How do we calculate this, and how can we use that law of conservation of energy to help us in those calculations? So if we were in class, I would give you the whole derivation of how do we get the potential energy formula and the kinetic energy formula. But instead, since we're not, I'm just going to give them to you. Potential energy is equal to m times g times h. And we should probably be pretty familiar. M is going to be mass. G is the acceleration due to gravity. And H is the height above the reference point. And most of the time, that's going to be the ground. So potential energy, there's a formula, equals m times g times h. Kinetic energy, Ke, has to do with motion. So of course we're going to have a velocity in here. So we have 1/2 mv squared. So v is your velocity and m is still your mass. So there we go. There's our two formulas. If we take a look at our ball example again, let's just draw this again. Right here, here, and here, there was my ball. Let's talk about the actual energy. Let's give this some units. Let's say the mass of this ball was 1 kilogram, and the height right here to here was 1 meter. And here it's 1/2 meter, and here it would be, of course, 0 meters. So the mass is 1 kilogram. Well, let's figure out what would our energy amounts be. Here, the kinetic energy is 1/2 mv squared. What's the velocity? It's 0, right? This part is 0, so 1/2 times 1 times 0 squared is 0. So it has no kinetic energy, which is what we said. Now we have the formula to back it up. What about the potential energy? Well, it's m times g times h. So 1 times 9.81 times 1 just gives me 9.81. And I haven't talked about units, but when we talk about energy, we're talking about mass times gravity. That's going to be kilograms times meters per second squared, which we know from before is newtons. So that's newtons. The height was in meters, so we have Newton meters, and I do believe we talked about that. That would be joules. So we have 9.81 joules. Here we had 0 joules. What about when it is halfway down? What's our kinetic energy and what's our potential energy? We said it should have some of both, right? So kinetic energy, we don't actually know. Let's not do this one. Let's do this one at the end. What is the, let's look at potential energy first. Potential energy is mgh. My mass is still 1. Acceleration due to gravity is still 9.81, but my height is 0. So what is my potential energy? It's 0 joules. What did we say when we looked at this before? All of my energy got converted to kinetic energy. So if we take a look at the initial, what was my total energy here? My total energy was just my potential energy plus my kinetic energy, which was 9.81 plus 0, which is just 9.81 joules. What about over here? Well, we know that, guess what? The total energy still needs to be 9.81 joules because the law of conservation of energy says that regardless of interactions within the system, the total energy remains the same. So if we had 9.81 joules before, we have 9.81 joules afterwards. If my potential energy is 0, what does that tell me about my kinetic energy? Well, it means that my kinetic energy has to be 9.81 joules, because those two together must sum to 9.81. So we could go one step further and say, okay, well, if I know my kinetic energy, how fast is it going? How fast is the ball moving? And we've done that question before. We've done it using kinematic equations, right? We would say VF squared equals VI squared plus 2AD. We do VF equals the square root of all this, which would be your initial velocity was 0 squared plus 2 times 9.81 times 1. And you would take the square root, and that would give you 4.4 meters per second. Not so tricky. So there's my answer here. That's my final velocity. But we could also find the final velocity using an energy calculation. What do we know about kinetic energy? We know the formula for kinetic energy is 1/2 mv squared. And guess what? We know our kinetic energy. We can rearrange this for v, and we know everything else. If we rearrange this for v, we'll have v equals, I'll do the rearrangement here. We want to get rid of this 1/2, so we're going to multiply by 2 on both sides. So that'll cancel out, multiply by 2 over here. So we have 2ke equals mv squared. We want to get rid of this m, so we'll divide by m on both sides. So we have v squared equals 2ke divided by m, and we don't want v squared, we want v, so we'll take the square root of both sides. So we have v equals 2ke divided by m, and I'll take the square root. If I do that, 2 times my kinetic energy, so 2 times 9.81 divided by my mass, which I said was 1, and we take the square root of that. 2 times 9.81 divided by 1, take the square root of that number, we get, unsurprisingly, 4.4 meters per second, which is the same thing we had above. Two different ways of calculating the same thing. Now you might say, Mr. Osberg, why would we ever do this then if we already know how to do the kinematic equation? Well, there's going to be some instances where you cannot use the kinematic equations because you don't have enough information. So you would actually have to do this energy calculation. The important thing that you keep in mind as you're going through these is the law of conservation of energy. So I'm not going to give you a ton of formulas other than the potential and kinetic energy formulas. But the important thing to remember is in an isolated system, the total energy remains the same before and after. So that means your energy before, the sum of your energy before, has to equal the sum of your energy afterwards.